Probably the most important gas law of all is called the ideal gas law. And you don't really need to know this, but this is a nice summary of Boyle's, Charles, and Avogadro's as far as proportionality. Volume is inversely proportional to pressure. Volume is directly proportional to temperature. Avogadro's law also tells us volume is directly proportional to number of moles. So do make sure you understand these relationships. If we combine all these, though, in a proportionality, we get something that looks like this, and that led to the development of the ideal gas law. The next two pages are out of order, so I'm going to flip 2 slides from now. All right, so going back to this slide, the different values for R, okay? And again, you can see it just depends on the units you're using. The more common unit that we'll use for gas laws is liters, atmosphere, moles over Kelvin, and it's 0.08206, okay? And onward. So the relationship that I just showed you, proportionality, scientists put in what we call a proportionality constant, which is called the universal gas constant. And the value of R, the universal gas constant, that makes all of these proportions work is R. So there are a table of R values or gas constant values, and you will select the one you use based on the units of all the other variables in the equation. So now I'm going to go back to the last slide. All right, so here we go. Let's talk some more about the ideal gas law. PV equals nRT. That gas law describes what scientists call ideal behavior. And most gases, under most circumstances, behave ideally, and it's okay to use this equation. We'll talk about the exceptions. But in general, a gas is most ideal if it's under low pressure and if it's under a higher temperature. Okay? Low pressures and higher temperatures are things that make gas molecules far apart, and that gives them what we call their ideal behavior. When do you use an ideal gas law, and when do you use the combined gas law or some rendition of it? Well, it depends. If you have the properties of a gas right now, only under one set of conditions, you will use the ideal gas law. Okay? It only has one set of conditions. If you're reading a problem that's telling you you're changing one or more variable, you're changing the pressure or you're changing the volume, that's when you want to use the ideal gas law. Here's an example that would use the ideal gas law. They have given you volume. They have given you number of moles. The number of moles right there should tell you it's ideal gas, because number of moles does not show up in the combined gas law. They give you pressure, and they ask for temperature. That's just a setup using the ideal gas law. PV equals nRT. You've got to have your table of R values on hand to work these problems. I will give you R values on any quiz or test, but while you're working your problems, you're going to want to have that handy. You can try to work this problem out on your own, or you can go to the next page with me. All right, all you have to do is plug and chug. Okay, pressure they gave you, 1.85 atmosphere. Volume, 47.3 liters. Moles, 1.62 moles. Here's the R value that has units that match all the units that were given to us in the problem. And we're solving for T. Rearrange this equation and solve for T. Remember that temperature will always be in Kelvin. Be careful, because some problems may try to trick you and ask you for the answer in Celsius. If that's the case, you need to subtract 273 from the Kelvin value. So if it asks for Celsius, the answer would be 385 degrees Celsius. All right, only a couple more quick concepts. Molar volume. That, by definition, is the volume of 1 mole of gas. Okay, molar volume. This is where we get our 22.4 liter value that you may have seen before and that I mentioned at the beginning of this lecture. If you take the ideal gas law and you rearrange it so that volume is on one side by itself, and you plug in all of the standard conditions that we've learned for gases, and so that would be 1 mole. Our value doesn't change. Standard conditions for a gas are 0 degrees Celsius, which is 273 Kelvin. Standard pressure is 1 atmosphere. When you plug all those values in, you get that the volume of a gas under standard conditions is 22.4 liters. And we say that 22.4 liters is the molar volume of any gas under standard conditions. STP means standard temperature and pressure. So what that means in real life is that if you have a set volume of any gas, doesn't matter what the gas is, and in this case we're setting the volume at 22.4 liters, you will have the same number of particles of gas inside that volume, regardless of the identity of the gas. Okay? And it so turns out that in 22.4 liters, you will have exactly 1 mole of whatever gas you have. That's a really important concept to have grasped. All right, and the final concept, density. You know density to typically have units of grams per milliliters. Doesn't have to be. It could be grams per milliliter, but it's usually that. In any case, it's a ratio of mass of a substance to the volume it's taking up. The mass of 1 mole of anything is called molar mass, just like the volume of 1 mole of anything is molar volume. Okay? How do you get density? This is a formula you will have to memorize. Density is molar mass divided by molar volume. So check this out. Molar mass has units of grams per mole. Molar volume has for a gas has units of liters per mole. So when you simplify this, let's see, moles cancel out, and you would get density units of grams per liter. So again, remember, write it down on a note card or something, that if you're asked to calculate the density of a gas, you take its molar mass and divide it by its molar volume. So here's an example. Here's the density of helium gas and the density of nitrogen gas. Helium has a molar mass of 4 grams per mole. Let's get that from the periodic table. If we're under standard conditions, which this problem told us we are, the molar volume of any gas is 22.4 liters, and therefore the density of helium gas is 0.179 grams per liter. All right? So, and here's the density of nitrogen, calculated a similar way. Notice nitrogen is one of the diatomic gases. That's why its molar mass is 28 and not 14. All right, so using the density of gases and the molar mass, there's a couple other forms of the equation that you need to be familiar with. This is going to ultimately lead you to an equation that allows you to calculate the molar mass for a gas, and you won't need to do the derivation, but I just don't want to pop it out of nowhere for you. So if you rearrange the ideal gas equation, you can get it in this form, which is moles over volume. Moles over volume sounds kind of like density, doesn't it? The amount of something in a certain volume. And so starting with that, if we were to make some substitutions, if I were to ask you, how do you relate mass and moles of a substance? You would, I hope, tell me that moles equals the mass of the substance divided by its molar mass. And so if I just substitute this relationship into this formula for N, so wherever there's moles, I'm going to say mass over molar mass. Remember, that equals moles. Okay? I still have to keep the rest of my equation, the V, and pressure and temperature. Okay, and so now if I rearrange this equation so that I have mass over volume on one side and everything else on the other side, that's how I got the equation for density. That's another way to solve density. But I want you to pay attention to this because in a minute you're going to have to solve for molar mass of a gas. All right, so I rewrote the equation just as it was written on the last page. Okay, kind of another form of the ideal gas law. This is density. If we rearrange it, like if you had a problem that asked you to solve for molar mass, this is what you would get. This is how I remember this equation. I've told you my memory isn't so hot. So what I remember is that mangy mutts, MM, put dirt, okay, kind of ignore the R, over their P, okay? Mangy mutts put dirt over their P. That's how I remember that formula. Here's an example. All right, so let's say you're on the test and you're reading this question, and if you're like most students, you're like, oh my gosh, I have 25 gas laws I have to remember. I don't even know what's what. Here they're giving you pressure, they're giving you volume, they're giving you temperature. So you might start writing the ideal gas law, but you see density. Whoa, and there's molar mass. Another name for molar mass is molecular weight. Anytime you see density or molar mass, you need to write that cute little formula I told you how to remember. So before I do anything, I'm going to say, okay, mangy mutts put dirt over their P. That's it. That's all you have to do to solve this problem. Now plug everything in. And there we go. They gave you the density. Here's our value. Make sure you convert temperature to Kelvin. And here's pressure. So if you plug all that into your calculator, you get that molar mass is 33.5 units for molar mass or grams per mole. And that is it. Make sure that you don't lose your common sense in these problems. If you get a molar mass that's like 0.5, that's impossible, okay? So remember molar masses on the periodic table, and the smallest atom, hydrogen, has a molar mass of 1. So you need to get molar masses that are within reason. Sometimes you can even kind of try to figure out what the gas is from its molar mass, but I really don't know in this one. That's it for this portion of gases, and there'll be another lecture coming up going over diffusion, effusion, and a few other facets of gases.